Our second speaker was unfortunately unable to travel here unexpectedly, so she has submitted a recorded talk. We will not have questions afterward. If you have questions, we ask that you email them to her directly or through the Krell Institute. We'll make sure that she gets your questions. This speaker is Margaret Lawson from the University of Illinois at Urbana-Champaign. Her advisor is Bill Gropp in computer science, and she did her practicum at Lawrence Livermore National Lab.
Hi, my name is Margaret Lawson, and today I'm going to be talking to you about accelerating discovery from high-performance computing applications using descriptive metadata management. So my work has really been driven by a number of insights. So one, analysis often requires loading in data from short and long-term storage. This can be for a number of reasons, including that not all analysis can be done in situ or in transit, and that analysis is often iterative. So scientists have to go back to the same data sets multiple times. In addition, loading in this data takes a lot of core hours. HPC applications can produce really exorbitant amounts of data. Even almost a decade ago now, a 24-hour run of XGC1 could produce 100 petabytes, and these numbers have grown dramatically in the last 10 years. In addition, due to the I/O bottleneck, it can be really slow to try and load in these large amounts of data, and the I/O bottleneck is only expected to get worse now that exascale machines are arriving. And in addition, in many cases, scientists don't need all of this data. Many analyses only require scientists to have data sets that contain particular features of interest or the data pertaining to these features. For example, in astronomy, scientists are often interested in analyzing particular kinds of supernovae or halos, or in a climate simulation, a scientist may be interested in tracking tropical cyclones. So what they really care about is the data associated with these features. Finally, scientists have many different ways to identify these features of interest, which range from pretty simple things like gradients and thresholds and entropy to more complex techniques like machine learning and visualization. So the main opportunity driving my work is that if we can help scientists only load in the data containing features of interest, then we can dramatically speed up their analysis and therefore accelerate discovery. So in particular, we can store what I call descriptive metadata, so high-level information about features of interest that scientists have identified using existing analysis techniques, and then provide scientists with an efficient way to search this metadata to identify the relevant features for a particular kind of analysis they want to perform, and then finally allow scientists to determine what data is associated with those features so they can just load in the relevant data. And so this is really important because, to make it simple, the time spent performing I/O is time not spent making discoveries. Without these savings, and as these data set sizes grow larger, many discoveries could be delayed or never made at all if we don't find ways to make improvements. As you guys are probably pretty well aware, HPC is used for many critical tasks like improving medical treatments or helping come up with an effective vaccine during a pandemic, developing safe and efficient energy sources, and improved prediction and planning for natural disasters and climate change. And again, just to reiterate, exascale machines have arrived, are going to become more prominent, and with such large machines, these problems are just going to continue to get worse. The overall takeaway, so if we can reduce the time scientists spend loading data for analysis, you'll be able to make discoveries that would otherwise be impossible. So while there is this really great opportunity, there are some issues with the current state of the practice, namely that existing descriptive metadata solutions are limited to only storing features that are associated with entire files, efficiently supporting a single kind of analysis, or supporting only a particular application or very small group of applications, meaning that there's no general descriptive metadata solution that exists, which I define as a system that can help scientists working with a wide range of applications, analyses, and mesh types to restrict their reads to data subsets containing features of interest. So with the general solution, more scientists can benefit and more discoveries can be made. So despite all the benefits that a general solution can offer, there are a number of challenges that have to be solved first. So first, the system must be able to efficiently map for metadata describing features of interest to the associated data. Once scientists have identified the features that they care about for their analysis, they need to know what data they actually have to load in for us to have these gains. And this is particularly challenging for applications with complex mesh types, since with simple meshes, in the easiest case, a regular mesh, you can just really easily map from, oh, a feature exists in this spatial location, this is the data we need to load in. But with complex mesh types, or in the hardest case, an unstructured mesh, you actually have to perform a spatial search to know what data points even fall in a particular spatial region. In addition, we need substantial flexibility and or extensibility to support the wide range of applications, analyses, and mesh types used in HPC, since there is such a diversity. And finally, HPC systems must be high performing, have good scalability, and require minimal storage overheads. Since, again, in HPC, scale can range from a single node to thousands of machines. High performance is essential since scientists have limited core hours, and minimal storage overheads also really important since, again, nodes do have limited amounts of memory, and applications in HPC tend to already be pretty memory intensive, so scientists often have little to spare. So the first question I looked at in my research is the problem of supporting complex meshes and performing this metadata data mapping for them efficiently in a way that's scalable and has minimal storage overheads. So the solution I developed to this is that when scientists identify features of interest, we can store bounding boxes for them. And then when we want to map from these features of interest to the associated data, it's now translated into a range query. And this is an area of computer science that's been studied for decades, with a lot of really clever solutions developed. So in particular, we can use an in-memory mesh index to obtain an O of log n search complexity with no storage overheads. And since this index could be created on demand, the solution would be portable and not affected by data layout changes. This solution would also allow us to parallelize the mesh index creation and searching. Again, scalability, really essential to high performance computing. So to actually go about trying to implement the mesh index, the next question I looked at is, do any existing range query indices provide the level of performance, scalability, and memory overheads needed in HPC? And the approach I took to answering this question was to analyze 20 state-of-the-art spatial index implementations that were free, open source, and were supported for C or C++. And overall, I found that there were 2 libraries that performed really well across the board. Namely, Boost has an R tree that performed really well, and Siegel also has an R tree that performed very well and was particularly good at supporting applications with non-rectangular mesh elements. The next problem I looked at was how to enable efficient storage and retrieval of descriptive metadata while providing sufficient flexibility to support the wide range of applications and analyses used in HPC. And the solution I developed really tried to attack this from many fronts, but included at a high level, having a domain-independent metadata model, support for extensible user-defined metadata, and at a lower level, using a flat namespace, separating values that do and do not need to be efficiently searched to allow for improved indexing, and supporting the storage of values of flexible data type to reduce storage sparsity. And again, once I came up with a high-level solution, I turned my attention to the implementation. So the question I looked at was, do any existing storage backends provide the level of performance, scalability, and storage overheads needed for HPC descriptive metadata workloads? And my overall approach to answering this question was first to develop a set of evaluation criteria used to determine which databases are best suited to HPC, and then evaluated the most promising databases using a wide range of descriptive metadata workloads. I found that overall SQLite is actually the best suited to HPC. It can achieve really high performance, really good scalability, particularly when using a separate database per core, and has the lowest storage overheads. So after I tackled these 2 questions, I looked at solving the more general problem of creating a general descriptive metadata solution. So I incorporated this metadata data mapping and metadata storage solution to create this system into an application-ready solution that scientists can integrate into their workflows today due to its free, permissive, open source license. The library called Impressa is implemented as a header-only C++ library and has two components, the metadata management engine and a mesh index. So the metadata management engine uses embedded shared nothing servers. This allows the application to, the metadata management to scale with the application. And SQLite's also incredibly low memory overheads, which works well for embedded solution. And this also eliminates the need to send metadata messages across the network, which eliminates many potential performance bottlenecks and other reliability issues. And then for each piece of metadata, users can store a wide range of information, such as what type of feature it is, like a cyclone, what application run, time step, and variable the feature is associated with, the spatial location of the feature, if it's a spatial feature, and additional information about the feature. So for example, for a tropical storm, a scientist could store like the wind speed associated with this. And the system also supports a wide range of analyses, including global, temporal, spatial, multivariate, and value-based analyses. And scientists can perform a wide range of searching within these categories, including performing exact matches, range queries, and substring matches for text information about the feature. And as discussed before, so the metadata data mapping solution involves creating an index on the mesh. I talked a little bit about this before, and it is maintained separately from the metadata management engine to allow scientists to use it for additional kinds of analyses that can benefit from range queries, which can be extracting regions of interest, like say near the application boundary. For example, in neuroscience imagery, maybe a scientist wants to extract data pertaining to different regions of the brain. It can also be used for things like subsampling or aerial interpolation. So maintained separately to allow it to be of even greater benefit to scientists. So to evaluate the system, I used two different machines at Sandia National Labs, both of which have 128 gigabytes of RAM per core. One had 36 cores per node, one had 56. And the main difference was that one used a all hard drive Lustre parallel file system, and then the other one had an all SSD Lustre parallel file system. Since SSDs are starting to become more prominent, I wanted to test the performance differences across both types of parallel file systems. And in addition, for the evaluation, I used hybrid MPI OpenMP programming with one thread per core. Since, again, my goal was to develop a general metadata solution, I used 3 highly varied data sets with their associated metadata sets and meshes, one from a computational fluid dynamics simulation, henceforth abbreviated as CFD, one from a climate simulation, and one from the dark sky simulations, which are actually particle tracking. So this allowed me to test the ability of my solution to work both with applications that use standard meshes and even a broader set of applications that maybe don't use meshes, but do track information about objects within an arbitrary space. And these data sets, metadata sets, meshes were highly varied in terms of the total number of application runs, time steps, variables, metadata types, total metadata count, and number of files per application run, varying from approximately 10 to 80 million pieces of metadata generated from application runs using anywhere from around 1 to 2,000 cores. And again, these were designed to reflect some of the variability found within HPC and to test the most complex mesh type, specifically unstructured mesh. So the overall testing harness followed a basic pattern. First, writing phase where all metadata was written. Again, we would expect that scientists would typically find most metadata during the application run when the data for the application is being written. And then a reading phase, which consisted of a number of steps. So first, the mesh indexes are created, then the metadata databases are opened, then the metadata is queried to find the features needed for various analysis routines. And these queries varied depending on what was scientifically meaningful for each of the 3 applications. And then for each metadata query, so once we found our features of interest, then the mesh indexes were queried to find what data is associated with these features. And then the associated data was read in. Again, so simulating scientists identifying what features they need for analysis, determining what data to load in, and then loading it in so they can perform further analysis on exactly the matching data. Overall found that write performance was very good, with ranging from around half a second to, in the worst case, still under a minute, with really good scalability, typically in upwards of 80%, often closer to 90 or 100%, both for weak and strong scaling. For reading, again, despite all the many steps involved in this process of involving like the mesh index and querying the database and reading in the data, total time was in the 10 to 30 second range for all data sets, and found, again, really good scalability, particularly for the CFD and dark sky data sets, ranging from around 70 to 100% in all cases. For the climate simulation, we actually found lower scalability, typically 50% or less, both for weak and strong scaling, which overall demonstrated that scalability really suffers when a data set has a large number of temporally decomposed files, which led to parallel file system contention. So in the climate simulation, there were actually hundreds of files per application run and over 20 runs. So and since they were broken down temporally rather than spatially, we actually ran into cases when multiple different processes would be attempting to read data from the same file at the same time. So this kind of contention is not inherent to this approach. However, the system could exacerbate parallel file system issues by performing large numbers of simultaneous small reads across multiple different files. And overall, our goal is to accelerate analysis, and we found that in most cases, the system can help speed up analysis by orders of magnitude, often very dramatically, and that there are only a small number of cases when we failed to produce speedups, mainly when we had to read in all the data. So there were a few cases where scientists were interested in features that covered all of the simulation space. So in that case, there's no opportunity to accelerate analysis by reducing the amount of data read in. And then also there were a few cases where scientists were interested in reading a single variable that was very small, less than 1 megabyte. And in those cases, again, we were unable to produce speed up since reading in the entire variable took 0.04 seconds. So there just wasn't an opportunity there to accelerate it by doing the metadata query and then reading a subset of it, since the overall data size was so small. And we also found very good results for a metadata data mapping solution, with the processes being able to build the mesh index really quickly. Again, we were able to parallelize it very effectively. So each processor core could insert 3 to 7.5 million mesh vertices per second. And then also really good mesh search throughput, again, achieving really good parallelization, with each core being able to search anywhere from 5 to over 200 million mesh nodes per second, with as expected, better throughput being obtained for larger meshes. So overall, we found that we were able to achieve really good build and search performance for the mesh index and excellent parallelization. For storage, we actually found that due to the indexing, which was again designed to accelerate the queries, that we actually could have relatively large storage overheads compared to the metadata set size, ranging from around 30 to 120% overhead. However, these in all cases constituted really small storage overhead relative to the data set size, under 1% in all cases. So since typically metadata size will be dwarfed by the data set size, this should not be a problem, but investigating lower storage overhead solutions is an area of future work. So overall, in this work showed that a general descriptive metadata management solution will be an essential component for exascale systems, since it enables analyses that would otherwise be impossible by allowing scientists to only load in the data that is needed for analysis. And in the future, I plan to look at additional classes of applications, in particular maybe AMR applications, to improve the metadata data mapping for arbitrarily shaped mesh elements and features of interest, and to integrate the system Impressa with existing application workflows. Thank you. And if anyone wishes to contact me with questions or comments, I have included my email.